Okay, so hello everyone. So I would like to first thank the organizer for this great meeting. I mean, it's for me in Firenze, and I really love the city. So I hope next year and the year after I can come also. So the talk of today is called Geometric Resolution of Schwarzschild Horizon. It's the name of the last paper we wrote, but during this talk, I will try to give a kind of an overview of the recent development in our work with like those collaborators from Johns Hopkins University and also people in Saclay. So the idea was to try to construct fundamental constituent of theories of gravity and understand what kind of new physics they will provide beyond GR and more specifically new black hole physics. Okay, so I will do some kind of motivation which are close to what Nick said. So black holes have been a great theoretical laboratory for many years towards the world of quantum gravity. Essentially because it's, even if it's predicted by general relativity, it's at the center of strong conflicts between GR and quantum mechanics. And those conflicts need to be resolved by a consistent theory of quantum gravity. So first, in GR, black holes are made of a curvature singularity, which needs to be resolved by new degrees of freedom from quantum gravity. And even worse, the scale for which quantum gravity should emerge is not really Planck scale away from a singularity. It is expected to be at the horizon scale. Indeed, Hawking told us that horizon are slightly problematic because it makes the black hole evaporate and behave like a destructor of information. So you expect the new physics at this scale from quantum gravity also. And last point, it's about the microscopic description of black holes. We know that black holes have a huge entropy, which a priori should underlie a description in terms of an immense number of microstates from quantum gravity. There is no known form of matter that can reach such degrees of freedom. For instance, the number of states into Sagittarius A is just this black hole is already way much larger than the number of states of radiation in the CMB. So black holes at the very end is kind of a new portal. It doesn't work well. Oops. New portal into a new gravitational phase of matter that needs to be explored, and it will tell us a lot about quantum gravity in general. So this quantum gravitational phase of matter will provide new quantum gravity states at the scale of the horizon. And the question I'm trying to address is essentially what are those degrees of freedom from quantum gravity that make the black hole, resolve the singularity, the problem of the horizon, and the entropy. It's pretty ambitious. So to describe those states, they are a priori very quantum, but we can, as Nick showed us, you can try to consider the coherent quantum gravity states that will have a description in terms of classical gravity. So it has been shown in the supersymmetric paradigm that a lot of microstates of the black hole can be described as either called microstate geometries or more generically gravitational solitons. So those are just geometries which are entirely regular, smooth, and horizonless like a star, but it's emerging from pure degrees of freedom from quantum gravity. So they are coherent states, and also they resolve the problem associated to black holes. They resolve the singularity, the horizon, so a priori we will not have the problem of evaporation and destruction of the information. And how does this resolution works is essentially we have like well-defined recipe to make those objects. They use dynamics of extra compact dimensions, topological deformation of these dimensions, and at the very end, some electromagnetic flux. So in the supersymmetric paradigm, we have a clear view of how it works, and Nick's talk was just showing that there have been a lot of progress in describing microstates of black holes using those objects, and also some non-trivial dynamics. So the question I tried to address the last few years is, does this kind of answer also be extended beyond supersymmetry? Can we have coherent quantum gravity states manifesting like as a gravitational solitons beyond SUSY? And can they be used to resolve horizons of non-extremal black holes? Okay, so during this talk, I will try to describe new techniques to build gravitational solitons out of vacuum. directly from Einstein equation. Then I will add electromagnetic flux, which is a necessary step, and see how we can build solitons that resolve horizon of Schwarzschild. And at the very end, if I have time, which I will describe some gravitational properties. Okay, so let's start by the beginning. We want to describe solitons in gravity. So a soliton in general is a perpetual state that can exist in nonlinear theory. So the best example we have is kind of a wave propagating at the surface of the water that is never dissipating due to nonlinearity of the propagation. But in general, a soliton describes a fundamental state of your theory, which is entirely regular and non-trivially excited. So general relativity or gravity is the best example we have of a nonlinear theory of gravity. So we can ask, does this soliton object exist? So let's start by GR. Can we build from a vacuum GR in 4 dimensions an object which is smooth and horizonless, made of a pure deformation of space-time, like a soliton without any matter on top of it, which is finite energy and stable? So for this, it's pretty easy. There are no-go theorem. You cannot find any solitonic object. It's either black holes or flat space. So let's try to add some ingredients that can be fundamental. Let's try to add now, for instance, a gauge field on top of the problem, and think about turning on some charges there and build a solitonic object. Same answer. There is strictly nothing. You cannot build any gravitational solitons in GR. So despite the complexity of GR, it's kind of hard to deform it without ordinary matter. So there is a no-go theorem that tells us that there are no gravitational solitons in general relativity. So my research is about constructing this object. So we have an answer, and it's pretty simple. There is nothing, and we can head there. Now, obviously, the end of the story is not there. No-go theorem in general in physics are more pointing out degrees of freedoms that we need to add or emerge naturally from quantum gravity to build those objects. So the first degree of freedom that emerges naturally from string theory is the existence of extra compact dimension. So let's try to deal now with similar kind of setup, 4-dimensional infinite space-time, but we just add a compact circle such that at each point of the space-time here, I have a compact direction, which is a priori small to still have kind of an effective 4D physics. If this compact dimension is always finite as a constant size everywhere, nothing special happens. Essentially, you have a cylinder coupled with a 4D infinite space-time, and if I have a little man walking there at a certain point in my extra dimension, I will not see anything, and I get just 4-dimensional physics. But now if I make this size of the circle vary, non-trivially, this will back react on my 4-dimensional space-time as if matter were there, but obviously this deformation is purely gravitational. There is absolutely nothing that produces that except some deformation of these extra dimensions. So here now my little man will walk at the same point, but he will be attracted as if some matter was there, but there is nothing. It's pure gravitational deformation. Okay, so now can we build gravitational solitons out of it? And the answer is yes. You need to impose what we call topological deformation of this extra dimension. At certain point, the circle degenerates to a point, and this will produce a topological soliton. So for my observer now, what I have done is I capped the circle at a certain radius RB, such that if I am a little guy again walking straight line, I will meet this hand to space-time, and while I'm still going straight line, I'm going backward. So a bit like a Michael Jackson thing. But at the very end, what I'm doing is I'm meeting a minimum radius of size RB square, which define what we call a bubble of nothing. It's a soliton produced from vacuum Einstein equation in 4D plus 1 circle, and it's just a bubble that attracts me, deforms space-time, but there is absolutely no matter out of it. So here, from this kind of simple picture, we have a good idea of what we need to do to build gravitational solitons out of gravity. And those will provide new phase of matter, new gravitational phase of matter that we just need to build. So here, just like some picture, the idea is how to construct them. So the idea, what we want to do is to construct them straight away from Einstein equations. So we need to solve Einstein equation non-trivially and build such a topological soliton. So the problem with Einstein equation is usually, it's kind of famous. You usually need to know the solution before solving it. So this is kind of annoying because they are very complex, but a lot of people in the past derive great methods to find explicit solution out of them. And the first thing we can try in vacuum again is called the Weil formalism. So the Weil formalism is you take four-dimensional GR in vacuum, no matter, and you assume axis symmetry such that like you can decompose your space-time in rho and z and a phi circle. And the only thing is nothing will depend on phi, neither time, so everything will be static. And Weil observed that here Einstein equations are pretty gentle and everything, oops, too far. Okay, everything decomposed in linear equations. So we know how to solve that, such that the field here, W0 and nu, can be solved exactly in this rho z plane, such that W0 is essentially a product of Schwarzschild factor, like 1 minus 2m over Ri, where Ri is a distance to a source on the z-axis. So you will actually produce a chain of black holes in 4D of mass mi. I can add as many as I want because everything is linear. And the Ri here is a distance to each of them. So by doing that, I will have a chain of Schwarzschild black hole on the line. The only thing which is important to point out is because they are super attractive, if you want to make the structure static, they will be separated by a string with negative tension to prevent them from full collapse. But this is just to show that we can actually solve exactly Einstein equation if you do it properly. So now the question is, can we build topological solitons by adding extra dimension on top of the game? So it has been shown by Anand, Parallel, and Real 20 years ago that if you add extra dimension in the game, the linear system of equation still remain. You will have more function in the game, like more W0 for the time and Wi for each circle. But at the very end, each of them will satisfy harmonic equations that you can solve by this similar kind of function. So here, if all the W's are 1, essentially I get flat space, and the picture here on the right is just what is the behavior of those extra circles. I just took 2 at the z-axis, rho equal to 0. But at the very end, what I can do is first build the previous geometry I've been talking about, the bubble of nothing. So the bubble of nothing is just produced by one source on this axis, making like one of the circle to degenerate to 0 size, such that I get a metric which is mostly looking like Schwarzschild, but the direction which is shrinking is a compact circle and not the time. So it's a Euclidean version of Schwarzschild, but it's a perfectly smooth bubble of size 2m. As soon as 2m satisfies some regularity condition, regularity conditions that fix the size m here in terms of the extra dimension size. But at the end, this is solvable, and since we have linear system of equation, we can build a more complex object, which is made of several bubble of nothing on top of each other on the z-axis. So here, if I make, for instance, on one piece of my z circle, I make this circle to shrink, and then here I can also make this circle to shrink, and there also. Everything is linear, so I have the full system of equations that I can solve and build a solution. It will be at the very end a bound state of bubble that are separated once again by a string with negative tension. But one thing which is kind of remarkable, and we noticed like in this paper, is as soon as you glue those objects, the string, which is kind of a singularity, disappear. So if I glue now those 3 top bubble of nothing on top of each other, they will merge into a more complex object, which will be made of several degeneracy of those extra compact dimension, and I will have a kind of a new exotic object, which is entirely regular and smooth, and without horizon. So this family of solutions are just built from classical theories of gravity in vacuum, nothing special. No matter, and you have an object at the very end in D dimension where you have several circles that are degenerating. You have kind of usual Schwarzschild form, and you have an H here, which is kind of complex, but at the end, you can derive everything analytically and have these gravitational solitons explicit. The only condition is those m, which is the size of each individual constituent in your system, will be constrained by the size of the extra dimension. And this h, which I didn't give here, is a kind of complicated function that accounts for different interaction between each of the atoms inside there. But we can say, okay, here we already have a gravitational soliton that solve Einstein equation in higher dimension, and a priori look like a 4D object, which is interesting. And indeed, if you reduce to 4D by compactifying along those guys, it's actually a black hole plus bunch of scalar field from those deformation there. But the black holes is singular in a sense. You have such a metric at r equal to 2m. You have indeed a time which is degenerating, but it makes everything degenerate. Like you have the S2, which is degenerating. You have non-trivial singularity at r equal to 2m. But at the very end, this object is very indistinguishable from an object which is not like an astrophysical black hole. It's a singular guy of mass m/2. And you perfectly resolve this singularity as you go in ILD with those extra dimensions. So, okay, it's already good. I mean, we made non-trivial gravitational solitons that look like singular black holes just from Einstein equation in vacuum. Yeah. Yeah. Everything is at r equal to 2m. It's a bad one. Yeah, it's a very, very bad singularity. No, nothing. Yeah, it's just given, yeah. I mean, the only thing is like those small m, which are the individual constituent, will be constrained by your extra dimension size. So it's like given. But at the very end, you can put atoms on top of each other and make an object that grow like that. So m can be as big as you want as soon as you put more. Okay, so we can say
given capital M can include as many mi.
Yeah, it's linear equation, so you can take as many as you want, and everything is analytic. So you just it's pretty simple. I mean, after the regularity are non-trivial constraint on the mi, but yeah, from the form of the metric, it's an arbitrary number, and it solves Einstein equation straight away. Say again, sorry. Yeah. Quantum field? No, I mean, yeah. No, everything shrink here. I mean, that's why you have an apparent singularity at r equal to 2m. It's just because the scalars are actually also diverging there, and just telling you that you're making some circle to degenerate. So that's why it's like usually when you have some kind of coordinate degenerate singularity, which are regular on top, if you compactify, you get something which look very singular. But actually, if you uplift, you get something perfectly regular and smooth. This one you mean, or this one? I mean, this one has no horizon, so as Vori, it appears somewhere. I don't know. Yeah, I mean, for me, it's just very singular object. So okay, so the problem with the solution is that they are very unstable, and ultimately we want something stable to just discuss a bit some physics. And it has been shown that the bubble of nothing is a top of the hill solution in a sense. If you derive a gravitational potential, the solution will be there, such that as soon as you perturb a bit the object, it will either grow and eat the full space-time or decay back to vacuum. So just mean that we need another ingredient. And I mean, Nick's talk, we already saw what this is object. This new ingredient is electromagnetic flux on top. So we can understand why electromagnetic flux is needed, just because like the energy, as soon as you add flux, is usually scaling like the integral of the norm of the field strength, which goes like q squared over r squared heuristically. So this term is a kind of a contraction resistant term. It will prevent the full system from full collapse. So you will have kind of a tail in the gravitational potential that will increase, such that you can expect a minima down the, yeah.
Because
Yeah.
Before it was low.
Yeah. Yeah, here it's a bit the same, yeah. Oh, yeah, there are a different way to see why charge is needed here. So by this contraction resistant term, you can hope to have a solution here down the potential that will be at least metastable. So okay, it means that in the previous construction where we solve Einstein equation, we will need now to add electromagnetic flux, and we can expect gravitational solitons that will be stable. The question is essentially, can we construct them? It's always the same thing with Einstein equation. Can we solve them? So this leads us to the second part about doing similar kind of object made of topology, but now adding charge on top of it. So now the challenge is even bigger. We need to solve Einstein-Maxwell equations in higher dimension, which are even more nonlinear. But once again, some clever people in the past did great work where we can just get inspired and use the result. So in 4D, for instance, the Ernst formalism, which is a bit based on the Weil formalism, assuming similar kind of symmetry, where everything is depending on rho and z, and you have an isometry along phi and static object. It has been shown by adding a flux now, like a U1 flux, simple. The equations are not linear anymore, but they are at least integrable, such that we can priori extract non-trivial solutions out of it. And once again, a lot of people have derived non-trivial solution out of that, which will correspond in 4D to black holes on a line once again, but they can have non-trivial charge. So from inverse scattering inverse scattering method, some people have derived very ugly and non-trivial solutions that correspond to an arbitrary number of Rice and Armstrong on a line that solve this system of equation. And once again, it's pretty much the same game. You have non-trivial black hole there with a string with negative tension in between them. We also observe that we can restrict to a system of a branch of solution where things are still linear. So it's useful because it will be simpler to extract solution. And we call that a charge Weil solution. The only condition is the mass over charge ratio of each of your source here is constant for each of them. But at the very end, if you assume that, you can have a pretty compact system of solution for this warp factor Z and A, such that like this W here keep the usual form we had before, like the Schwarzschild factor, and you have a B here which control the mass over charge ratio, in a sense that mass over charge ratio of each of the constituent here will be given by Cosh B, such that you can take an arbitrarily vacuum limit by taking B to infinity. It's you going back to the Weil system before, and by taking B to 0 limit, you go to the BPS supersymmetric case where everything is extremal. Yeah, like the condition for having linear solution is to impose a mass charge to be constant.
Can you go away from this?
Yeah, this solution above, which is way more complex, is doing the thing. But here it's just to keep linear solution because you can put arbitrary number of guy on the line. Well, this one, if you take 3, it's already half a page. So, okay, but once again, there are plenty of methods in 4D. The question is, can we extract that and generalize in arbitrary dimension? So what we have done is essentially try to understand if I put in setup where I have non-trivial flux and extra compact dimension, which are the framework that still allow Ernst equations. So what I've done is essentially classify non-trivial frameworks that decompose into a set of Ernst equations, then will allow non-trivial resolution of those equations. So like, for instance, one of the setup which is used in some of our paper is like you start with M theory on a T6 times S1 with 4 infinite dimensions. You turn on very non-trivial flux, essentially 4 type, sourced by M2 branes or KKM monopole. And here you will have non-trivial set of equations that are solvable from Einstein-Maxwell equations. But also, I mean, to make the link about the framework Nick talked about before, you can also do the same with D1, D5P, KKM on in type 2B. And similar, you will have the same kind of equations. Here, I will just present a simpler system where I kill some charge. I just take D1, D5 on a rigid T4 with 2 extra compact circles. So the metric is as follows. I have 2 extra circles, Y1 and Y2. I have a 3-dimensional base here with the same symmetry as before and a time direction. But now I allow non-trivial D1 in D5 flux. So HD5 is a gauge potential for the D5 flux, D1 for the D1 flux. And I have non-trivial definition of metric components here where ZD1 will couple to the gauge potential, etc. So what we notice essentially is here, if you plug this ugly metric into Einstein equation, everything will decouple in nice sectors where we know how to integrate. Essentially, you have a sector, for instance, for the D1 branes, and the sector for the D5 branes, where each of them will give Ernst equations. Then for the W here, it will be also vacuum Weil equations that we need. We know how to solve. So at the very end, we have 4 different sectors of equation, but people in Ford working in GR have been allowed to extract solutions, so we can just use them to build topological solitons now. So what we have done, once you have this decomposition, is build non-trivial solution. Yeah. Yeah, here I just put the dilaton away, but you can add the dilaton otherwise. Yeah, it has an overall volume. By rigid, I mean just like there is no internal deformation, but like it can grow with. Yeah. The thing is, as soon as you have this equation, you can take the best solution you want for this sector. That is like, I mean, people have derived it in 4-dimensional GR. And you do the same for this one, and you put all together to make some bubbling geometry. They will have charge, yeah. So let's discuss the simplest object we can build. Yeah.
It is the sources are electromagnetic or
this one is electromagnetic. It's a D1, D5. D1 is electric and D5 is magnetic.
What point of view of the 4-dimension is electromagnetic?
Yeah, but you can take also like full magnetic. I mean, you just have to dualize in different frame. Okay, so the simplest object we can build is what happened if I just source my previous system with just one rod, like a bubble of nothing, but I add charge on top of it. So we call this object topological star. And here the solution is pretty simple and spherically symmetric. So you can restrict to just 5D, because you will just play with one circle degenerating to 0 size. And this is what you get, essentially. You have 2 parameters, RB and RS. You have a Schwarzschild factor in front of the time, a Schwarzschild factor in front of your extra dimension. You have a round sphere, and the radial direction is a mix of those 2 Schwarzschild factors. So at the very end, it looks like a black hole in the sense that R equal to RS, I have an horizon. But if I take RB bigger than RS, I will make this circle degenerate before the horizon form. So I cap off my space-time just before having a black hole. So at the very end, my geometry will be entirely regular and smooth, and at R equal to RB, such that at R equal to RB, I have a non-trivial sphere of size RB square. So this object requires non-trivial charges to be turned on, like Q is equal to the product of those 2 guys. And it makes sense in the sense that if I take RB to 0, I retrieve Schwarzschild, while if I take RS to 0, I found the bubble of nothing. So here we manage through the system to build a non-trivial object directly from Einstein equations, Einstein-Maxwell, which is inherently non-supersymmetric in a sense that Q has no constraint compared to the math. But the only problem of this object is the regularity condition, which will fix RB and RS in terms of the size of this extra dimension Ry. So you can understand of Ry as the periodicity of this Y circle. But if you want something which is relatively 4D, you want Ry to be very small. So for instance, if I take Ry to be of order 10⁻³ the Planck length in 4 dimension, this object, topological star, will have a mass which is smaller than a mole of protons, which is 10⁻⁻36, the solar mass is very, very compact. But at the very end, calling it a star was a bit ambitious, and it's more a kind of very small particle out of gravity degrees of freedom. So ultimately, we have this nice solution. The goal is to make a macroscopic object now. So the best way to do that is try to solve equation by merging them on top of each other. Yeah. Yes, if you compactify to 40, yeah. Yeah, like if you compactify to 40, you will have a square root of 1 of this guy in front of everything, and it will be singular. Yeah, it's a bit like the previous vacuum solution I showed. Sorry? Yeah, in 4D, yeah. But it's resolved by the coordinate singularity in IR. Okay, so we have seen that the equation of motion decomposes nicely if you make everything axis symmetric. So here you can just use equation of motion and hope to build a kind of bound state of topological star using those different extra dimension where you can make essentially merge those different objects on top of each other. And at the very end, you will build an object which will grow. I mean, it's kind of playing Legos with those topological star. It will grow in size as you put more and more on top of each other. So the first thing we've done is essentially use charge Weil formalism because it's based on linear equations. So here you can put as many as you want and then make the object to grow in size. And the equation was solved analytically thanks to the fact that the charge Weil formalism is a linear set of equations. So what we have observed for that is we have constructed a smooth bound state of topological star, an arbitrary number. The only requirement is that the charge of the object is proportional to the mass because each of these ingredients have the same mass to charge ratio. But we make the statement that the size of the overall object scales also with the number of ingredients. So you can build a macroscopic object even if the extra dimension is small. We have also studied the gravitational properties of this guy. It's really looking like a non-extremal black hole with singular scalar on top of it, but everything gets free from singularity and horizon in 6 dimensions. And the last statement, which is also important here, is like 6D setup, but those objects have a clear origin as brane transition from string theory in top-down framework. So the solutions are ugly and complex, but the thing is we can derive them analytically. And you can just plug in the best software you want, and you can derive some gravitational properties out of them. Okay, so the problem with that is even if it's linear, the charge of the object is non-trivial because we put topological star with the same mass to charge ratio. And ultimately, if you want to build the best non-extremal object and resolve the horizon of this one, you want to try to do Schwarzschild and then have an overall charge which is 0. So to do that, it leads us to the third part. How I'm doing with time? I have no idea. Okay. So now I'll try to do a similar kind of step, but trying to build an object which is neutral from far and somehow look like Schwarzschild. But first, we need to discuss a bit what will be resolving the Schwarzschild horizon using extra dimension and flux. So the goal is we will try to take Schwarzschild neutral vacuum solution, add extra dimension on top of it, and add flux from branes in string theory, and turn those objects on such that it will create a non-trivial topology, regular, and everything that replace the horizon into those new objects. The problem of doing that is essentially if you turn on non-trivial deformation of compact dimension, you will have, from a 4D point of view, scalar hair. While if you turn on non-trivial brane flux, you will have a non-trivial gauge field from the 4D-dimensional perspective. So what you can try to do is turn them on such that they are very like a high value at r equal to 2m. So you have non-trivial topology there, and try to die fast. But the problem with Schwarzschild is you want to die them super fast in a sense that you want a solution which look like vacuum up to like a small scale above r equal to 2m. So I mean, having a leg which is like 1 over r is not fast enough. You want 0 and then boom. So this is kind of hard. Like in supersymmetric setup where microstate geometry has been built, it's a bit simpler in the sense that the extremal black holes in the setup have already scalar hair, scalar tail and flux, such that you already have some kind of tails for black hole, and resolving it is dividing this 1 over r into sum of constituents. So you can do that, but here the thing is you have absolutely no tail. Everything is neutral in vacuum up to a small scale above, and then as soon as you go in, you make them explode. So how to proceed for Schwarzschild? You want something which is making deformation of extra dimension and brane flux that are mostly zero as soon as you're a bit away from the horizon. So what we have done is we managed, let's say, we did half of the work. Yeah.
But if you don't want a charge from away, so you have at least that kind of multiple. So you have issue of the stability.
No, but like the thing here, I'm saying I don't want dipole. Like dipole will like die like 1 over r squared. I want also some of the charges, but the dipole needs to go away somehow.
But also higher.
Yeah.
So.
Yeah.
But if you put charges, very good attract. If you would do Pierre, I would guess that you could manage the charges.
Yes, the stability. I mean, the stability of the solution I will show here. We don't know yet. It can be unstable.
About the stability of charges inside, how they are stabilized.
Yeah, I have the same question. I don't know, but we indeed like what we will do is to put non-trivial charges, and it's static. The solution is static, but it's unclear if you perturb. I have the feelings that it can be stable, at least perturbatively, but it needs specific derivations that I didn't do. Okay. But so yeah, we need something where the flux, okay, the flux dies very fast, just away from r equal to 2m, and also the scalar. But the thing is, we didn't manage for the scalar, so we defined a solution which is called Schwarzschild scalar wall, in a sense that it has a non-trivial scalar leg in 4D, which will use it to resolve in higher dimension. So we define this family of solution, which is essentially looking like Schwarzschild in black, but there is a non-trivial scalar on top of it, which is like 1 minus 2m over r here, that non-trivially back react on the geometry and deforms the two sphere of the object. So it's a family which is essentially made of an horizon at r equal to 2m, but this horizon is slightly singular. So the scalar has like just make the singularity up to r equal to 2m. But here the question, with this setup, we managed to ask, like, can we resolve the horizon here at r equal to 2m? So what we did is, for instance, you can first embed this solution, just this one, in M theory as a vacuum solution, where the scalars arise from torus deformation. So it's kind of a complex solution where you have non-trivial coefficient into like a T7, non-trivial warp factor. But if you compactify that up to 4D, you retrieve this object. What you have just done is making the circle, like the torus, to collapse. We're just telling you that you are essentially playing with extra dimensions to replace the horizon by new bubbling structure. Okay, so here we ask, okay, can we resolve this r equal to 2m horizon? So we will do it step by step. The first thing I have done is essentially replacing first the locus by a bubble of nothing, by just making a bubble of nothing of size L, making one circle in M theory to shrink. And I have an object which is entirely regular. But as I said earlier, this object, if I compactify to 4D, doesn't produce the right redshift. I have like a square root, while for Schwarzschild, I want 1 minus 2m over r. So we need new ingredients on top of the game, which we can do by using the fact that our equations are integrable. What I've done here is adding two, on top of the bubble of nothing, two charged objects, point-like, which are M2 branes, essentially, at the pole of the bubble. One is charged minus Q and one is charged plus Q. So everything remains neutral. So the solution gets slightly more complex, but at the very end, you can derive it analytically. And the thing which is pretty nice is that these Z functions that coming from the fact that the charge back react on the geometry is mostly looking like 1 minus L over R, just as soon as you go a bit above R equal to 2M. Moreover, the flux is also mostly zero everywhere, even if it seems that you could get a dipole, but it's strictly zero up to a small scale above R equal to 2M. So why is that? Essentially is even if here those two charges are geometrically well separated by a distance L, their physical distance, if you take into account the distortion of space-time, is incredibly small. It's just like wraps, like squeeze the sphere a huge amount. So it's like a donut, essentially. They're super close to each other. So that's why you manage to kill the charge, kill the flux at all order, a bit away from the horizon. And at the end here, the 4D reduction does the job. You have a new Z here, which is mostly 1 minus L over R. So you bring a factor there, which is like the Schwarzschild factor, 1 minus L over R. So the last step of the reduction is to resolve the charge object into bubble, but it's just a further step where you nucleate bubble there and replace. Once again, the solution is fully derivable, but I mean, it's not really interesting to detail how they look like. But at the very end, this is a kind of first example of solitons directly made from Einstein equations that resolve the horizon of a Schwarzschild black holes plus a scalar tail. So next step, obviously, we'll try to get rid of the scalar tail, but for the moment, is what we have. Okay, so I will just very briefly talk about some gravitational property of those guys. So we build those interesting, 5 minutes perfect, interesting geometries out of Einstein equations. The goal now will be, okay, what are their gravitational characteristics if you try to compare to astrophysical black holes like Schwarzschild. So those objects, they are not made of any matter. So they will not radiate like star or anything. So the property are really related to the deformation of space-time they are producing. So for instance, their apparent image, their apparent image will be related to the gravitational lensing effect produced by those objects. And second, we can also get interested into gravitational wave emission. We had like a nice talk yesterday about QNMs, and here is just about just about trying to get the signal if you excite those gravitational solitons and try to compare with a black hole. I think I will not have time to discuss that, but I will try to talk about the lensing. So for the lensing, the goal is to send some geodesics into our background. The thing is, all those gravitational solitons or topological solitons are entirely irregular. So you expect if I send a light, it will come out somehow. So to do that, we need to compute geodesics trajectory out of our background, and then try to understand what you will see as an observer sitting somewhere. So like black holes, they are very intense deformations, so they will produce photon ring. So for instance, you will have a photon ring circumscribing the object, which will be a bit like the shadow of the soliton. But the thing is here, all light that goes inside, because there is no horizon into our soliton, will not be absorbed and will be bouncing on the non-trivial geometry there and come back. And the question is, what will you see as an observer? So what I've done is I built a ray tracing code to try to simulate what will be seen from an observer sitting at a certain distance from my object by putting a celestial sphere around the object and sending light rays from everywhere and reconstructing the picture. So here is a usual kind of picture like patch we use there just to show how the lensing work. So if it's flat space in front of my observer, I just see the back of the sphere, it gives this kind of thing. But now the question, so for Schwarzschild is kind of famous. You see the shadow in front, and you have some rings where it's just like turn half like a deviation angle, which is half of the space, and as soon as you go close to the shadow, you have several turn around the object. So now for the Schwarzschild scalar wall, which is the singular object I've been discussing before, you see it's pretty much like Schwarzschild, but because of the scalars that squeeze the sphere, the difference is that it's a bit squashed. You still have a shadow, but it's squashed on the pole. For the smooth resolution of this, so the gravitational solitons that is resolving the horizon of this guy, you have the exact same kind of deviation around, but inside, all light that goes in will do some funky trajectory and at one point come back. So the thing is, at the very end, like the photon rings match very well in size, so the characteristic is pretty much reconstructed, at least for the shadow of the object. Yeah. No. Like, I mean, this you can do in 4D, but this one is regular only in higher D. I mean, where it's smooth, so this one is like at least 6. That's why I had to build my own, because usually the codes that are existing are 4D, that require 4D, while here you need like the full thing. Okay, here is just like some nice picture when you replace this sphere by some kind of star patch, and you get pretty much the same kind of figure, but the thing is what from inside goes back in some way. The thing is, we argue that if you go beyond the problem limit, you expect that the photons that go in here will endure an incredibly high redshift, such that it will somehow be absorbed by the geometry, as Nick argued before, and then be like radiated. I mean, will be re-emitted with a huge redshift, such that the luminosity will decrease significantly. So beyond the problem limit, you should put a kind of darkening factor in front of what goes inside, and give something which is now almost indistinguishable from those three objects. Yeah. Yeah, it will interact with the. Yeah, exactly, and then it will be re-emitted as own radiation of the object, which this one, as soon as it go up, will be incredibly so redshift. I mean, very low energy essentially. Yeah. But this is a very heuristic argument, and to do that, it will be hard. Like the time it takes for the photons to escape, here, like, it's huge. I mean, it depends on the zone. I mean, in the paper, we have the time scale, time delay of the photons here. It's pretty huge. I mean, this is infinite, and here it's usually like 1 over the resolution scale, something like that. So you can make it very, very small and trap for a very long time. Okay, I will skip the rest. Here, it was just about doing some kind of accretion disk simulation. If you put an accretion disk, which is like just basic light around, I mean, nothing very accurate, you get a picture which is very much similar. And if you take into account the darkening factor, once again, it's very much similar. Okay, so the QNM, I will not have time. What we derived here was essentially try to understand, if you try to derive the QNM of a black hole, natural astrophysical black holes, as we have seen yesterday with Victor's talk, the frequency are mostly given by the shadow. So here the question is, if I replace it by a soliton, which is having the same shadow, what happened? You just replace the horizon by some new structure there. So what we observed essentially is two kind of difference. First, you retrieve some kind of black hole modes that localize there, but fundamental modes also localized deep inside. The thing is, which were interesting, is this black hole mode there doesn't have the same imaginary part of frequency, so you expect a kind of damping factor difference. So the fact that the decay time of the black hole modes is not the same, you will expect, for instance, that it can decay slightly slower. And then you have the usual mode that localize at the microstructure. Usually they give echoes, but as Nick said, they can get you can get rid of them if you can account for back reaction. Yeah. Yeah. I mean, it's like the imaginary part is usually next order, and for me, it's really kind of a cavity effect. Like if I put an horizon here, this will kind of absorb. I don't know, but the thing is, like the imaginary part, which just tells you how the mode decays. There, you have less absorption. You will decay slower. I think that should affect. Not really, because like those modes are usually like the black hole modes, so there's early time. Like they have this guy, like the real part is the same as a black hole. So the frequency, it oscillates the same way. But here's the thing I'm saying is it's slightly shifted. Like it's not only the property of the light ring when you replace the horizon by something topologically smooth. Okay, so just to conclude very quickly, or I have a bit of time. Okay, so the thing we have seen here, if you deal with Einstein equation in higher dimension, you can extract non-trivial objects, which are gravitational solitons, and they exist in number, a bit like the supersymmetric partners, so that's good news. And the goal is try to understand what they can tell us as a new phenomenology and maybe fundamental role as a new black hole microstates. There are many aspects to explore. I mean, we have also tried to do some kind of embedding in anti-de Sitter to understand the holographic profile of those objects. Then also you can try to think about adding more and more degrees of freedom into the Einstein equations to build more generic solitons, like spinning solitons will be kind of the next step, or also Chern-Simons interaction in the gauge fields. Then, I mean, there is an open question, which is, okay, now we have the solutions, you can derive them analytically, what they are, what are the gravitational signatures of these objects? So can we make any kind of comparison with astrophysical black holes that can be relevant? And then because those objects are non-trivially non-supersymmetric, there is a question of stability and existence. Can we nucleate them in physical process like a universe, or so at late stage of matter collapse, to understand a bit of phenomenology? So I stop there, and sorry if I'm a bit late.
Well, I just would like to have your thoughts on something that I think Nick yesterday was asking, which is if you take two of these stars and you merge them, what exactly is going to stop them from collapsing to a black hole? Do you have any thoughts on that?
I mean, this you can compute. For instance, I was thinking about computing tunneling amplitude if I take like two of those objects, and you can derive the tunneling amplitude to the same guy with like the sum of the charge, which is glued. This you can do, and you have a non-trivial amplitude. So a priori, there is other phase that just black hole, just by to have an explicit understanding of the process, how those topology creates. You don't really know, but there is non-trivial amplitude from one to the other, which is entirely derivable.
Right, but at least in 4D, if you use the hoop, a reasoning in terms of hoop conjecture, you take two of these guys, they should.
Yeah, but I mean, the sheer existence of those objects is also against the hoop conjecture. So just individual objects are.
Well, not really, because the compactness is still below the Schwarzschild compactness, right?
It can be arbitrarily close. I can
Yeah,
find,
but it doesn't contradict the hoop conjecture just because of that, right? Their existence.
I mean, you mean like it can collapse? Yeah, I see.
Yeah.
No, this is. I mean, we don't have like a specific dynamical process where we can illustrate that. But they are definitely states. They are metastable. Like for instance, the topological stars. So you can expect that if they exist, they can stay there. And then like how they can be created, you can compute tunneling amplitude, but it will not also tell you how they form exactly. It will just tell you that they can from vacuum.
I just wanted to make a comment to Vitor's point. So the point is, those geometries, they should be thought more like a proof of concept that such things exist. Because, until a year ago, before Pierre and Ibu got onto this field, we had zero Schwarzschild solitons. We could not construct any one microscale geometries. Now I have a huge amount of them. Of course, in the supersymmetric examples, we know very well that you have a much bigger number because they're easier to construct, and then we know very well what's happening when you merge two of them. There's a huge amount of degrees of freedom, and the degrees of freedom just go into the whole phase space. But the whole idea that the black holes should somehow be magically formed, I think this just a 4D prejudice. And the moment you look at the full degrees of freedom of string theory, there's no place in the black hole in the phase space. There's a phase space of all these geometries, and there's no place where all of them can collapse into the black hole. There's not even such a place in the full string theory phase space. So this idea that things should collapse into the black hole is just a 4D artifact. Once you look in the full physics at the full degrees of freedom, there's no place for that.
Just want to add to that also. In my talk, I talked about this idea that horizons are an artifact of using an effective field theory. And to see microstructure, you need bigger theory to see the detail. It's the same deal. This belief that horizons form is simply because an artifact, I believe, this is propaganda of effective rather than something that can resolve the detail. So
let's start with now reading more for the second point. So just going up what you said. Even in higher dimensions, from the semi-classical point of view, why do you say that there is no room for black hole? Because black hole is a solution, is in the spectrum of the solutions.
It's not a solution. It's just that it's not the right solution in the sense of taking some ensemble average into the phase space.
No, that's fine.
I can't prove that as a statement.
Okay.
We have now huge number of examples and we've seen, in the supersymmetric phase space, we found four of them where there was generated and the horizon. How's this? Years of talk is going to be all about how that is wrong. We really now have a lot of evidence-based experience. But whenever it's simply
okay. No, but I think my comment was, even if there are a lot of states in which these things can collapse to, there is also the black hole solution. So from the classical point of view, if I collide them, a possible outcome could be a black hole. Then I agree that this is probably not what one should.
But if you look at the space, for example, in two kinds. I mean, the example is, again, when you collapse the things, it's up to the space space, you don't mark the space space. But there's no reason to expect a collapse. I mean, when you have many degrees of freedom, there's no reason for them to go into one place to solve the black hole. If you think about the whole space space, the black hole is the corner. If you have two objects in some other place in the space space, you collapse them, you have some big hard message for space space. There's no, it's very hard to get all these guys to go to one corner to become uniform on the photos, uniform on the sphere, get perfect symmetry and then get a variety.
So let's thank again Pierre. Let's take a